Okay, next property. Well, I have just mentioned that the autocorrelation value at 0 is in fact the second moment of the random process, expected value of x of t squared. And obviously it is non-negative because it's the expectation of a square. But also it represents the average power of the process. Now, in the deterministic domain, if you have a signal, let's say, which is a function of time, which is not random, the average power you can compute by integrating the second power of uh, the signal and taking its average with respect to time. But of course, in the random domain, we will have to deal with expectations because it's not a constant function of time, the random process. But we have the expectation of the second moment, which is associated with average power of the process. Okay. And next, we say that the autocorrelation function is a measure of the rate of change in a random process. What does that mean? The rate of change in the random process. Well, we will, for this purpose, we will look at this probability. Um, the difference between x of t and x of t plus tau. Okay, the change in the random process within tau time units. Okay, we will look at the probability that in magnitude, this difference exceeds some epsilon, where epsilon is greater than 0. Okay, of course, if you take the square of both sides, which we know to be positive values, the event doesn't change. So that is the probability that x of t plus tau minus x of t squared is greater than epsilon squared. Now, at this point, since this can be defined as a non-negative random variable, y equals um, x of t plus tau minus x of t squared. Obviously, this is a non-negative random variable, and we will apply Markov inequality to y. The probability of y exceeding a for some positive a value is less than or equal to expected value of y divided by a. That's Markov's inequality. So here we are applying this to this random variable y, and a is epsilon square. So if to obtain the expected value of y as defined here, you just expand this expression x of t plus tau squared, x of t squared minus 2 times x of t plus tau. Of course, this is the autocorrelation at 0, x of t plus tau squared, x of t squared. This is also autocorrelation at 0. And this here, as you see, 2 times autocorrelation at tau. Okay, so here what we have as the upper bound, 2 times autocorrelation at 0 minus autocorrelation at tau divided by epsilon square. So what we see is the probability that the value of the random process changes more than epsilon within tau time units is upper bounded by this quantity. Okay, 2 times Rx of 0 minus Rx of tau divided by epsilon square. So in this sense, we say that the autocorrelation function is related to a measure of the rate of change in the random process, how much it changes within a certain time unit. Okay, next we have Rx of 0. As we have mentioned earlier, the Rx of 0 value is the bound on the autocorrelation from above and from below. The autocorrelation cannot exceed Rx of 0. It also cannot fall below minus Rx of 0. Okay, so you have this tau axis. Let's say this is Rx of 0. This is minus Rx of 0. Okay, we say that, well, this is the peak point. Okay, you cannot exceed this, but occasionally, so whatever happens here, let's say at D, you again reach Rx of 0 value. In this case, the autocorrelation will be periodic. Okay, if Rx of 0 is equal to Rx of D for some D value, then the autocorrelation function will be periodic with period D. Okay, the proof of this is not that difficult. It's based on the Cauchy-Schwarz inequality. It's um, if I remember correctly, the square of the correlation is less than or equal to the product of second moments. Okay, I didn't show this, so I'm not going to give you the proof. If you're interested, you can have a look at Leon Garcia's book. There is a proof there, but essentially the proof is based on Cauchy-Schwarz inequality. And in this case, we call x of t, the random process x of t, mean square periodic, because then when you have this equality, this is satisfied, right? Because if you expand this, the expected value x of t plus d squared plus x of t squared minus 2 times x of t plus d. Well, you see this is the autocorrelation at 0. This is autocorrelation at 0, so I have 2 autocorrelation 0. And then this here, autocorrelation at d. So 2 autocorrelation at d. And I know that this is equal to this, so this turns out to be 0. Okay, so in this case, the expected value of x of t plus d minus x of t squared is 0, which is the reason we call such processes mean square periodic. Okay, so finally, if random process x of t can be represented as some constant, which is actually the mean, plus another random process, which is 0 mean, okay, expected value of n of t is 0, and the autocorrelation of n of t dies out when tau goes to infinity at the right and left extremes, okay? In this case, if you write the autocorrelation of x, it's obviously mu plus n of t, mu plus n of t plus tau, because, well, this doesn't depend on time. If you expand this, you will get square of the mean plus mean times expected value of n, which is 0, plus expected value of n of t plus tau, which is also 0, right? Plus from these, you get the autocorrelation of n, okay? So autocorrelation of x turns out to be square of the mean plus autocorrelation of n. And at the limits, if you look at both limits, we know that autocorrelation of n goes to 0. Therefore, the autocorrelation of x at both extremes, okay, will go to square of the mean. Okay, so what does this tell us? The autocorrelation function of any random process can have 3 components. It can have a constant component, which is due to the mean, which is non-zero. If the mean is 0, it will not have that component. If you are an electrical engineer, this would be analogous to the DC component of a signal, okay? Plus, it might have, well, it will have a component that dies out when tau goes to infinity. And it can also have, it doesn't have to, but occasionally it can have a periodic component based on this observation, okay? So the autocorrelation function can only have these components in it.